Listen, there's a specific kind of silence that happens in a locomotive cab when the world expects you to move and the physics say no. It's a quiet, heavy pressure that settles into the small of your back as the dispatcher's voice crackles over the radio, asking why you haven't cleared the block yet. To the outside world, a train is a singular beast. But to the person with their hand on the throttle, it's a temperamental ghost. In the early spring of 2026, as the April rains begin to turn the mountain passes into slick, emerald-tinted traps, this reality hits harder than any manual can prepare you for. You're looking at 60 million pounds of steel that refuses to move, and for a few seconds after the throttle comes up, nothing happens. It feels like a personal failure, a moment where the crew becomes the target of every cynical joke back at the yard office, because behind you sits an impossible deadline and a consist that stretches beyond the curve of the earth. The ridicule starts early in the break room. The old heads laughing about how the new traction control systems were supposed to make the job idiot-proof, yet here you are, stalled out while the schedule disintegrates. The buried reason for the struggle isn't always a mechanical failure. Sometimes it's just the sheer arrogance of thinking we've mastered the friction of the earth. As the frost finally yields to the damp warmth of the season, the rails become sweat-slicked and treacherous, mocking the thousands of horsepower humming beneath your feet. This isn't just a delay, it's a standoff between a human being and 30,000 tons of inert matter. You've got a 2-mile-long tail of coal or grain or intermodal containers, and every single one of them is whispering that they aren't going anywhere today. The weight is so immense that it seems to distort the very air around it. When you think of the scale, 30,000 short tons translates to roughly 27,200 metric tons, a chain of around 1,000 fully loaded freight cars, each one weighing close to 100 tons. That is not just a big number. It's a logistical nightmare that has been decades in the making, born from the constant push for higher efficiency and longer consists that have pushed our infrastructure to its absolute breaking point. Before anything moves, every single pound of that mass has to be convinced to leave a standstill, and the moment you think of it as one solid object, you've already lost the battle. It is a long, flexible, and deeply unpredictable system where every car, every coupler, and every wheel reacts slightly differently to the pulse of energy you're trying to send down the line. The cold open isn't about the victory. It's about the terrifying realization that you might be the one who breaks the chain, either literally or figuratively, under the gaze of a company that only cares about the bottom line and a clock that never stops ticking. The April thaw brings with it a specific kind of mud and moisture that gets into everything, including the psychological grit needed to handle a machine of this magnitude. You are standing at the edge of a failure that will be discussed in incident reports for years, and all you have to fight back with is a handle and a few grains of sand. This is where the myth of the machine meets the reality of the mountain. You've been told since training that these locomotives are the pinnacle of human engineering, gods of the high iron that can pull the world if asked. But as the rain drums against the cab roof and the ammeter needles quiver without rising, you realize the machine is just as vulnerable as you are. The impossible deadline isn't just a number on a clipboard. It represents millions of dollars in liquidated damages and a ripple effect that will clog the main lines from Chicago to the coast. You can feel the eyes of the superintendents in their glass offices, looking at the GPS pings that haven't moved an inch in 20 minutes. They don't see the grade, they don't see the dampness on the rail, and they certainly don't see the way the slack is bunched up like a loaded spring ready to snap. They only see a graph that isn't trending upward. The ridicule isn't just about your skill, it's about the very concept of the heavy haul, a buried reason why some engineers refuse the route entirely during the transition from winter to spring. They know that when the ground is soft and the air is thick, the rails act less like a path and more like a grease-coated slide. You are tasked with achieving the impossible, making 60 million pounds of stubborn steel forget that it wants to stay exactly where it is, and doing so while the entire world watches for a single slip. The pressure on the head end isn't just about the physical resistance of the grade, it's a crushing weight of corporate expectation and cold, hard math that starts to squeeze you the second that ammeter stalls. In the rail industry, time isn't just money, it's the lifeblood of a continent-spanning circulatory system, and right now, you are the clot. Every minute this 30,000-ton behemoth sits motionless, you are hemorrhaging revenue ton miles, and the ripple effect is already being felt 3 states away. Dispatchers are juggling dozens of priority intermodal trains, carrying time-sensitive electronics and fresh produce that need the track you're currently occupying as a very expensive parking lot. The slot you were supposed to hit at the next interchange is already gone, and the penalties for missing that window are written into contracts with the kind of ink that never washes off. But the pressure isn't just coming from the glass towers at headquarters. It's vibrating through the floorboards from the shop floor politics that define the life of a railroader. Back at the maintenance facility, there's a friction-filled divide between the grease monkeys, who maintain these high-tech locomotives, and the throttle jockeys, who run them. To the shop foreman, a locomotive is a collection of sensors and modules that either show a green status light or a red one. If the computer says the Siemens or GE Heart of the Beast is capable of 150,000 pounds of tractive effort, then in their mind, it is. If you can't get the train moving, they don't see a physics problem. They see operator incompetence. They'll point to the diagnostic logs and swear the machine is flawless, leaving you to wonder if the ghosts in the machine are only visible to the person holding the handle. This is the hidden war of the rail yard, the constant tension between theoretical engineering and the grimy, unpredictable reality of a wet April rail. Your reputation is being dissected in real time over the radio waves, where every other crew on the frequency is listening to your struggle, measuring your worth by whether or not you can coax this mountain of steel into motion without snapping a knuckle. The timetable is a merciless god, and it demands sacrifices that your equipment might not be ready to give. As the clock ticks toward the hour mark, the dwell time on your consist starts to flash red on a monitor in a dispatch center hundreds of miles away, triggering automated alerts to upper management. You can almost feel the air in the cab getting thinner as the silence from the dispatcher becomes more ominous than their shouting. They've already rerouted 2 hotshots around you, which means you've just become the lowest priority on the division. If you don't move now, you might be sitting here until the shift changes, facing a carpet dance in the superintendent's office tomorrow morning, where you'll have to explain why 60 million pounds of company assets were held hostage by a little bit of spring rain and a steep hill. The engineering is supposed to be the solution, but when the numbers on the screen don't match the feeling in your gut, the technology starts to feel like a cage. You're trapped between the digital certainty of the designers and the physical reality of a train that has decided it is no longer a vehicle, but a permanent landmark. Every attempt to notch up is a gamble with your career. Too much power and you'll spin the wheels, scarring the rail and earning a reprimand for excessive wheel slip. Too little, and you remain the laughingstock of the district. The politics of the locomotive cab are a delicate balance of ego, expertise, and the desperate hope that the machine will finally live up to the marketing brochure before the next train comes up behind you. As the mid-April sun begins to set, casting long, mocking shadows across the ballast, the realization hits that no one is coming to save you. You have to find a way to make 1,000 cars obey your command, or you'll be explaining this failure to a board of inquiry while someone else takes your seat in the cab. The machine is cold, the rail is slick, and the clock is screaming. To understand why we are still standing still, you have to look past the 4,400 horsepower painted on the side of that GEES 44AC and look into the brutal, unyielding math of the technical spine. Most people, even some veteran rail fans, make the mistake of thinking horsepower is the primary metric for victory. But in the exact moment of starting, horsepower is almost a ghost. Horsepower is simply the rate at which work is done once you're already at speed. What you need right now is tractive effort, the raw, visceral pulling force at the wheel-rail interface. The relationship is governed by a fundamental formula. Tractive effort equals horsepower multiplied by 375 and divided by your speed in miles per hour. When your speed is effectively zero, the math becomes a paradox of infinite demand and limited supply. If you plug in a crawling speed of 5 miles per hour, even a 4,000 horsepower locomotive is only pushing out about 300,000 pounds of tractive effort, which is barely enough to get a 30,000-ton train rolling on level, dry ground. But we aren't on level ground. On this section of the high iron, even a modest 0.5% grade adds 20 pounds of resistance for every single ton of freight. When you run those numbers, you're looking at an additional 300,000 pounds of grade resistance on top of the 120,000 pounds of rolling friction already working against you. That brings the total convincing force required to 420,000 pounds just to break the spell of inertia. You are staring at a 120,000-pound deficit, and no amount of shouting into the radio is going to change the laws of physics. If you cannot reach that number cleanly, the train stays dead. Then there's the thermal limit, a ticking clock that most people never see. When you're standing still or moving at a crawl while dumping massive amounts of current into the traction motors, they start to cook. Modern AC traction motors are tougher than the old DC units, but even they have a breaking point where the heat generated by the electrical resistance in the copper windings exceeds the ability of the blowers to cool them. If you hold a stall for too long, you risk bird nesting or melting the insulation, a catastrophic failure that turns a $1 million locomotive into a very heavy paperweight. This is where the power electronics, the IGBT modules and variable frequency inverters start their frantic dance, adjusting power delivery in milliseconds to keep you on the razor's edge of adhesion. But adhesion is a fickle mistress in April. Steel on steel usually offers a coefficient of about 0.35, but with the moisture currently coating the rails, that can plummet to 0.15 or lower. You can have all the power in the world, but if the rail is greasy, you're just going to spin the wheels and cut a burn into the steel railhead that the maintenance crews will have to grind out later. The odd failure mode that usually bites you in this situation is the sander system. A single clogged moisture trap can prevent the silica sand from reaching the rail, leaving you with zero grip on a 1% grade. A common field improvisation involves an engineer having to physically climb out and tap on the sander lines with a hammer, or, in extreme cases, rocking the train, carefully using the slack in the couplers to start moving one car at a time. It's a dangerous game of taking the slack, where you bunch the cars together and then snatch them forward, using the momentum of the moving cars to help jerk the stationary ones into motion. If you do it right, you look like a hero. If you do it wrong, you'll snap a Janney Type E coupler like a dry twig, because while they're rated for 300,000 pounds of continuous tension, the shock load of 30,000 tons of surging steel can exceed 3 million pounds in a heartbeat, literally tearing the train in two. This isn't just about moving. It's about not destroying the very infrastructure you're trying to navigate. The witnesses to this silent war aren't just the birds chirping in the damp April woods, or the impatient crews waiting in the siding behind you. The real witnesses are the silent, unblinking eyes of the event recorders and the telemetry systems streaming data back to a centralized server in real time. To a casual observer standing on a nearby overpass, the train is just a frozen sculpture of industrial might. But the paperwork, the digital log of every pound of air pressure, every notch of the throttle, and every ampere of current, tells a story of a machine screaming for traction against an indifferent landscape. This is where the myth of the unstoppable train meets the sober record of the telemetry sheet. Popular rail lore suggests that if you just have enough guts and enough sand, you can pull the moon out of orbit. But the records from this late April season show a different, more humbling reality. These logs reveal the exact moment the adhesion factor dropped from a manageable 0.30 to a catastrophic 0.08 as the persistent spring drizzle mixed with the fine iron dust and leaf mold on the railhead to create a lubricant more effective than grease. The myth says that a master engineer can feel the rail through the seat of his pants, but the record shows that even the most seasoned veteran is at the mercy of a traction control algorithm that cuts power the microsecond it detects a wheel slip to save the rail from being scarred. We love to talk about the legends of the 1940s, the massive big boys and the articulated mallets that supposedly conquered the mountains by sheer force of will. But the archival records of those same railroads are littered with reports of double heading and stalls on the grade that history has conveniently polished away for the sake of the legend. The records don't care about the cinematic glory of steam. They care about the fact that a 30,000-ton train today is nearly triple the weight of what those mythic machines were actually pulling in their heyday. When you look at the incident reports from the dispatcher's desk, you see the reversal of the narrative. It's not the lack of power that fails us. It's the inability to apply it within the safety envelope of the 21st century. The paperwork from this specific stall will show that the locomotives were operating at 100% of their theoretical capacity, but the physical environment had simply withdrawn its permission for them to move. This isn't a story of mechanical failure, but a record of mechanical limits being reached and then overtopped. In the yard, the old heads will talk about how in the old days they would have just burned it off and gotten moving through sheer aggression. But the digital record shows that such an attempt in 2026 would have resulted in 3 broken knuckles and a derailed mid-train helper. The myth of the lone engineer conquering the elements is being replaced by the reality of distributed power, a symphony of remote-controlled units at the middle and rear of the train that are the only reason we have a chance at all. The data proves that without those DPUs, pushing from the back and pulling from the center, the stresses on the lead couplers would have exceeded their 300,000-pound continuous rating minutes ago. The witnesses in the dispatch center see the train as a single yellow line on a screen that hasn't changed its coordinates. But the engineering record reveals a desperate, high-stakes coordination between 3 different engine sets miles apart, trying to synchronize their pulses so the train doesn't snap like a dry noodle. This is the ultimate reversal. The more power we have at our disposal, the more we are constrained by the very steel connections that hold the train together. We are no longer limited by the firebox or the boiler, but by the molecular grip of a steel wheel on a wet rail and the tensile strength of a casting of iron. The records show that for every mythic climb into the clouds, there are a dozen shifts spent staring at a load meter, waiting for the weather to change or for a miracle of friction to occur. It is a humbling realization that despite our 4,400 horsepower engines and our IGBT-controlled traction motors, we are still fundamentally beholden to the same physics that governed a horse and wagon, the need to overcome the weight of the world with the friction of the earth. Then, almost imperceptibly, the world shifts. It starts with the air, not the wind outside, but the sound of the valves under the cab floor. You've waited the mandatory 120 seconds, and in this damp April air, likely much longer, for the brake pipe pressure to migrate 2 miles back to the end of the train, ensuring those rear shoes have finally unclamped their iron grip from the wheels. You ease the throttle into notch 1, then notch 2, and you wait. You don't look at the speedometer yet. It can't even register a movement this small. Instead, you look at the load meter and you listen. Far behind you, in the middle of the consist and at the very tail, the distributed power units receive their commands via radio link and begin to push in perfect automated harmony. This is the payoff of modern heavy-haul engineering. The lurch isn't a single event, but a rolling wave of kinetic energy. You hear it before you feel it, a rhythmic metallic thunder as the slack in 1,000 couplers is pulled taut, car by car, over the length of 2 miles. It's the sound of 60 million pounds of steel waking up, a sequence of heavy, bone-deep clacks that sounds like a giant's heartbeat accelerating through the forest. Suddenly, the cab floor vibrates with a new frequency, and the GPS decimal point finally flickers. You are moving at 0.1 miles per hour, but in this moment, that is a victory greater than any speed record ever set on a test track. The 420,000 pounds of resistance have finally been overcome by the sheer, synchronized persistence of over 1 million pounds of available tractive effort. As the train gains momentum, the physics shift from static to kinetic, the coefficient of friction stabilizes, and the machine begins to reclaim its dignity from the mud. But here is the sober note we often omit for the sake of a good story. What took us 10 minutes to describe actually took nearly 2 hours of agonizing, high-stress labor to execute in the real world. Popular documentary episodes and high-speed YouTube breakdowns love to compress this history into a 30-second montage of smoke and noise, skipping the hours of sitting in absolute silence, the frantic radio calls to the shop foreman, and the slow, methodical wait for the air to clear the lines, car by car. We show you the triumph because that's what sells the mythic nature of these machines, but we rarely show you the boredom, the freezing rain dripping off the grab irons, and the sheer, grinding patience that defines the actual life of a railroader. In the real world of 2026, there are no jump cuts to the finish line. There is only the long, slow struggle against the inertia of the earth and the constant fear that a single surge in power will snap the train in two. True power on the high iron isn't just the ability to pull. It's the discipline to wait until the physics are finally in your favor, and the precision to apply exactly enough force to move the world without breaking it. We celebrate the mythic machines for their strength, but we should really celebrate them for their restraint. When you see those miles of cars finally disappear into the mountain mist, remember that it wasn't brute force that got them there, but a delicate, terrifying balance of engineering and human nerves. It is a humbling reminder that in the face of 60 million pounds of steel, the most powerful tool in the cab isn't the diesel engine or the traction motor. It's the person who knows exactly when to let it breathe and when to hold it back. It's easy to build a machine that can pull. It's much harder to manage a system that refuses to move. Did you expect the hardest part to be the raw horsepower, or did the limits of adhesion and coupler strength surprise you more?